Yeah, y'all ready? I will let y'all ask specific questions if you have any, but this is just a review. Everybody? Lucy? Is that correct? Oh, Thursday. This is Thursday?
Yes, Thursday, like I do tomorrow. If you guys can do the session, last night I said you will work out these,
Okay.
of what we did. Otherwise.
I will give you guys an opportunity to ask questions, but I want to go over this one first because I originally had, if you look at this one, reactions, limiting reactant quiz, I just had gobbledygook for answers, so I went back and fixed that. But I'll do this one real quick, and then I'll just, you guys can tell me if you want to go over, otherwise I'll just go over whatever, some random things. That question is, this is essentially a theoretical yield question, but this last one in that quiz makes you go one more step further and calculate the percent yield. The difference between a theoretical yield and a percent yield question, the theoretical yield is the long walk, so you still have to do the long walk, and then there's one more thing at the end to do. Grams of CL2, grams of F2, and grams of ClF3 are all mentioned. So you're going to need these. Cl, there's two of them, times 35.45 in the periodic table, 70.90 grams per mole. This is Cl2. F2, there's two Fs, 19.00 from the periodic table. And then there's ClF3. Cl, there's one of them. F, there's three of them. And 3 times 19 is 57. And that adds up to 92.45 grams per mole. So you're going to need those. I might give you those for the test just to save you a step. So look for the grams per mole. Okay, first, whether you're looking for theoretical yield or percent yield, this is going to be the first step. So you remember what we do first? Pick one. Pick one of these two. I usually just pick the first one just to be consistent. So you'll take the grams of that, 4.5 0.39 grams of Cl2. Just do that. That tells you grams of Cl2 down here. The Cl2 is 70.90 grams. More formally, is 1 mole. So there's that. F2 is 38 grams of F2 is 1 mole of F2. We're going to need that. And then the ClF3 is 92.45 grams of ClF3 is 1. We're going to need all of those before we get to the end. But first, we're comparing the two reactants. The grams of Cl2 is here, so we're going to use that. 70.90 grams of Cl2 is 1 mole of Cl2. Since we're comparing these two to decide which one is the limiting reactant, we're also going to be using 1 mole of Cl2 to 3 moles of F2, the molar ratio. So next, moles of Cl2, 1 mole of Cl2 to 3 moles of F2. This tells you moles of F2 goes down here. And now we're using this. 1 mole of F2 is 38. All right, and note, what you're given up here is how much you have. This is how much the problem tells me of F2 is there to react. Down here is how much I need. So what we're calculating is how much we need, and we'll compare it to how much we have. .39 times 3 times 38.00 divided by 70.9. And my calculator tells me, I'll go ahead and round it, 7.06 grams of F2. So that's how much we need, and that's how much we have. So what's our conclusion? This is how much we need of F2, but this is how much we actually have. That tells us that F2 is limiting, and necessarily if that's limiting, then this is excess. We have more than this than we need. If we had done F2 here instead of Cl2, we would have come to the same conclusion. So that's what I mean by pick one.
What is the number for how much F2 you start with?
This,
Like the actual, yeah,
2.94. Yeah, 2.94. Okay, so we've done step 1. Step 2. Theoretically. Okay, to find the theoretical yield, can I erase some of this? I need some space. So finding that F2 is a limiting one, we did that because we're going to use the limiting one to predict products. That was the whole point of doing step 1. Now that we know which one of these two reactants to use, we're going to use the F2. 2.94 grams of F2 tells you grams of F2 goes down here. 38 grams to 1 mole. That tells you moles of F2 goes down here. We were comparing these two before, so we used this ratio. Now we're comparing these two, so we've got 3 moles F2 to 2 moles ClF3. So now we're using that. Moles of F2 on bottom, 3, and then 2 moles top. That tells you moles of ClF3 goes on the bottom. Now we're using this, moles of ClF3. 1 mole of ClF3 is 92. This will tell us theoretical yield of ClF3. Theoretical yield is always a product. Limiting and excess are reactants. The theoretical yield is always about the product. All right, so that'll tell us how many grams we theoretically should get when we put this many grams and this many grams of the reactants together. 2.94 times 2 times 92.45 divided by 38.00 divided by 3. Okay. And I get to 3 significant figures. 4.77 grams of ClF3. All right, that's our theoretical yield. We need the actual yield to calculate this. It's actual over theoretical times 100%. That's your percent yield. So that's a fairly simple formula. So going from theoretical yield to percent yield is that simple. Where is our actual yield? This is the actual yield. This many grams of Cl2 and this many grams of F2 and 4.67 grams of ClF3 is produced. This is our actual yield. And again, the actual yield is always easy. If you're in lab doing this yourself, that's what the scale says when you measure your product at the end, no calculation. And if you get a problem like this, it's stated in the problem. It tells you this is how much was produced. So this is how much we theoretically should have gotten. This is how much was actually gotten. And they're very close. Actual over theoretical, so actual grams of ClF3 over 4.77 grams of ClF3. And notice this cancels and this cancels. It's frequently said that the percent yield is unitless. Technically, this is a unit, and it does end up over here. But this is what they mean. There's kind of no label there. 4.67 divided by 4.77 times 100 to 3 significant figures. That's the percent. So that was review of how to calculate theoretical yield, and then one more step to calculate the percent yield. I guess this is step number 3, calculate the percent yield. But this is the long walk, here and here. That's the long walk. You guys okay? Right, I wanted to do that one just because I didn't have the answers in for this quiz. Anything specific you want me to go over? You won't see me again until Monday, so. What should I go over? I should. Well, let's look at this. Yeah, molarity, okay. Molarity is another one of those that don't have up here. So some of these I gave you problems from the back of the book to do. I'll find those. That was all the way up in chapter 8. Those are right here, so let me write it down. No, that's dilution. I should write those down still. I wrote those on the board. Let me find them. 2 p.m. Probably later. They're on one of these videos somewhere. What day did I go with that? I want to make sure I give you the right ones. Monday, 2 p.m.
I have some of the questions written down.
What were the ones I gave you for malaria? Yeah, my videos are not working out. 8.2. Yeah.
Because I'm too late.
I wrote it at the top of the board, so I should be able to find it. Okay, it's going back far. Almost there.
Call me.
Yeah, I'll rework those. I just want to know what the numbers were. I can probably figure it out. Was chapter 7 So it's 21 section. It's these. Let me erase. These are the ones that I don't have quizzes for, that you have to look at the chapters to see the problems. And then, so for practice, you're going to have to look here. I'll go over those next. And there's also 8.2. Solution dilution. Those are the ones that I don't have quizzes for. It would just be more convenient if I had the quizzes on D2L. But since I've kind of run out of time to make another question database, just keep those for practice. And so let's do some of these. Starting with 21 and 22 are the most basic type of questions for this. calculate the moles of Na2SO4 in 9.56 liters. Okay, so this is A for 22. Notice grams are not mentioned at all. That means we're not going to need the grams per mole of this. And it really means that Na2SO4 is kind of superfluous information. It really doesn't matter what the solute is. This is a solute. Water is probably the solvent. Solute meaning the thing that's dissolved in the solvent. So when you don't see grams, the identity there really kind of doesn't matter. This is true of anything. But the definition of molarity is moles over liters, so this is all set to go. And 9.56. I'm going to say solution because this is liters, so I'll put dash solution there. And that'll do it. That's going to put you in moles per liter. You just calculate it out. 0.55 divided by 9.56. My calculator says 0.05. It says one more digits. But that's two significant figures. That's 3. So I'm really just keeping these two. The 5 rounds to 7. So I will leave it like this. Okay, so calculate the molarity. 0.55 moles of this, 9.56 liters. So I write it like this. The moles, I just write like this. The liters are like Na2SO4 dash sol for solution. If you calculate that out, you end at 0.58. And you just write the units like that. If you wanted this in scientific notation, you write it like that. Na2SO4 solution. These are the simplest ones. Slightly more twisted is go to 27. I'll do 20. I'll do sum of 27. Let's see, 27. This is A, 27A. I'll just go ahead and write it out. How many moles of KCl are in 0.556 liters of 2.3 molar KCl solution? You don't see grams anywhere, so you're not going to have to calculate grams per mole. Again, the KCl is kind of superfluous here. Do remember when you see the M, go ahead and write that out more formally as 2.3 moles of KCl in 1 liter. Moles over 1 liter is literally the definition of the M. So we'll use that. We'll use this as is. If I wrote it more formally, I would go 556 KCl solution. So this one is 0.556 liters KCl solution. Now we need liters of KCl solution on the bottom. And 2.3 moles of KCl. These will cancel and we'll end in moles of KCl. Potassium chloride. 0.556 times 2.3. Three significant figures, 2, so I'm going to go 0.13. And that's the answer. Scientific notation, or standard scientific notation. So if the problem says put your answer in standard scientific notation, you would do this. But this is still correct. It's just not in standard scientific notation. So that's how you do 27, and 28 is slightly different. You can skip 29 because they don't tell you the structure of ethanol. But I'll do 28. 28 is on the test, I would probably say how many grams. Just so I'm specifying the unit. And I would also tell you what glucose is. C6H6. C6H12O6, I'll give you that.
Actually, no. Yours that I wrote in lower than that.
0.500 There's the question. Mass is mentioned this time, or grams is mentioned this time. That means you're going to need the grams per mole here. Unfortunately, this is a huge molecule, so it's C6H12O, 6 of those. On the periodic table, you get 12.01 for carbon, 1.01 for hydrogen, and 16.00 for oxygen. 6 times 12, 12.1, 72.06. This is going to be 12.12. 16 times 6 is 96. Two, 06. So we're going to need that gram per mole. Okay, another thing is, well, let me go ahead and do this. you can go ahead and break this out more formally into 0.500 moles of C2H12O6 to 1 liter C6H12O6 solution. There's that. And I've got this more formally in grams of C6H12O6 to 1 mole. Grams and moles, so I don't have solution there. So that's the more formal version of this. And we need to be in liters here because that's the definition of molarity. And they gave us milliliters here. This is 0.1220 liters. Now I'll go ahead and add the formal part, C6H12O6 solution. Those are the ingredients to solve this one. I would start with this, 0.1220 liters of C6H12O6. Now we need one of these that has liters of C6H12O6 solution, and that's this one. It needs to be down here. 1 liter of C6H12O6 solution is 0.500 moles C6H12O6. Now we need moles of C6H12O6. 1 mole H12O6 is 180.18 grams of C6H12O6. That'll cancel down to grams of C6. C6H12O6. Maybe I won't use such a huge molecule test. 0.1220. Just because it's the simplest one, because I always put it over 1. If you do it that way, this cancels with this, and then this cancels with this, and you can even use it as a guide as you go. It would work out. I could take this and put it in the front, and it would still work out the same because it's just the rules of algebra. It's still just multiplying across the top, dividing the bottom. So I like to start with that one just because it makes, that cancels with the next one, that cancels with the next one, and you end up in those units. And you can even use it as a guide as you go across. If you just start with that, you know liters of this goes on the bottom. Only one of those has the liters. So you write it in, and that tells you moles of this goes on the bottom. Only one of those has moles of that, so you can use it as a guide too to build them. That's why I talk it through the way I do. So 0.1220 1220 times 0.500 times 180, 4.8, and that's it. There's nothing to divide. My calculator says 99998. This is exact. This is exact. This is exact. 5 significant figures, 3 significant figures, 4 significant figures. So we got to do 3. There's my 3. The 9 rounds the 9. It ends up being 11.0.
I have a question. If that were to say 2 moles of C6H12O6, would that 2 still be exact?
If it said what?
If it said 2 moles instead of 1 mole, would the 2 still be exact? I know it wouldn't ever say that in like the case of this problem.
You mean here?
There or like with the moles?
Here? When we do this, it's always per 1 mole, because that's what's on the periodic table. It's per 1 mole. So that'll always be per 1 mole. It'll either be this many grams to 1 mole, or 1 mole to this many grams, depending on which way you use it.
if we had a problem, like we were saying, like 2 moles or something, to 3 moles or something else, are those numbers exact?
Oh, yeah. Those that show up, the coefficients that show up in a reaction, those are exact too. So like when I had, what was it, 2 moles of ClF3 to 3 moles of F2. These, once I put them into the calculation, those are exact as well. I should have said that. Anyway, this one's ended up being 0 grams. Those are the variations on polarity. I think that's all of them. Let me look at 30 real quick. Okay, one more. 30 asks you for volume. All right, 30 up here. So 30 is although I'm more likely to say on the test, but just to make sure I specify the units. What volume of a, God, these huge molecules. This is sucrose, C12, H22, O11. What volume? A 2.00 molar. C12, H22, O11. C12, H22, O11. All right. This book likes its big molecules. C12, H22, O11, times 12.01, times 1.01, times 16.00. I better double check that. 12 times 12.01, 412. This will be 22.22, and then 11 times 16, 176.00. Add them up. 4, 3. I better do this. 144.12 plus 22.22 plus 176 equals 342.34 grams per mole. So we're going to need that more formally, 342.34 grams of C12, H22, O11 is 1 mole of C12, H22, O11. So we're going to need that because grams was mentioned. This. Okay. So we need the grams per mole because grams was mentioned. This turns into more formally 0.200 moles of C12H22O11 to 1 liter of C12H22O11 solution. So we're going to use that, and we're going to use this to 55.8 grams of C12H22O11. And I'm going to start with that. This has a numerator and denominator. This has a numerator and denominator. This just is the numerator. So that's why I start with that one. And if you start with that one, everything cancels across. H22O11. So I've used this. Now this one, which one has moles, or no, grams? I need, on the bottom now, I need grams of C12H22O11. And this one has the grams. So 342.34 is 1 mole of C12H22O11. That tells you moles of C12H22O11. 1 mole is already used this one. So now I have to be on this one. This one has moles. It's 0.200 mole of that to 1 liter of C12H22O11 solution. And that will make us end on liters of C12H22O11 solution, which is what we were asking for. What volume that is, how many liters? C12H22O11. All right, so that'll do it. 55.8 divided by 342.34 divided by 0.2. You get exact. 3 significant figures, 5. So I've got to have 3. My calculator says 0.814979926. 3 significant figures, the 9 rounds to 4, so 0.815. And that's this. So that's review of law. That's okay. What else do you think you want to cover today?
Was there like the solutions that we're going into?
Yeah. Solution stoichiometry. So that's this one, 41 and 42. And you'll be given the balanced reaction 2 Na3 PO4 3. So that's the reaction. Notice first, I haven't given you any examples where you're comparing over here. It's always just comparing the reactants. That was just to sort of cut off the information for test 1. Notice Na3PO4, CuCl2, that's the 2 reactants. Volume, milliliters, grams isn't mentioned, so you're not going to need the grams per mole. Okay, that's 150. Sorry, this is molarity. 0.150 molar. So we've got this. That more formally is 0.150 moles Na3PO4 to 1 liter Na3PO4 solution. So we're going to need that. This, to be complete, I should say solution here. Solution. That one is 0.121 moles of CuCl2 to 1 liter. Solution. So we're going to need that. This is 82.9 milliliters of this solution. I want that to be in liters because that's in liters. And this is 0.082 liters. Or more formally, or more formally, 0.082 or 0.0829 liters. 0.0829 liters of CuCl2 solution. So those are our ingredients. We don't need any grams per mole. Okay. This has a numerator and denominator. This has a numerator and denominator. We're also going to need this. The, 2 moles of this to 3 moles of this. Right that over here. Three moles. We're going to need that molar ratio too. Okay, I would start with this. Everything has a numerator and denominator except this, so I start here. So I need liters of CuCl2 solution on the bottom. That, and this. The only one that has liters of CuCl2 solution is that one. So 1 liter of CuCl2 solution, 0.121 moles of CuCl2. That means moles of CuCl2 should be on the bottom. We've used this, we've got this and this left. The only one among those two that has moles of CuCl2 is this. So 3 moles of CuCl2, 2 moles. Now we need moles of Na2PO4 on the bottom. We've only got one of these left, it's up there, and it's got moles of Na3PO4. So moles Na3PO4, 0.150 moles of Na3PO4 to 1 liter. Put solution on it because it's a volume. What volume of Na3PO4, or I might say how many liters on the test, just to specify which unit I'm talking about. That'll do it. That'll cancel down to liters of Na3PO4 solution. Na3PO4. 0.0829 times 0.121 times 3 divided by 3 divided by 0.150. My calculator says that's exact, and this is what you were just asking me. These come out exact, these coefficients, so that's exact, that's exact, that's exact. 3 significant figures, 3 and 3, so we need to be a 3. There's 3, the 8 rounds to 5, so 0.0446. Standard scientific notation would be if you're not asked for standard scientific notation, that's perfectly correct. That's in standard scientific notation.
So on the test, is it going to be mostly scientific?
Sometimes I'll ask for scientific, sometimes I won't. I tend to not ask that much. But scientific notation will be in there in its own right, in its own separate question, like turn this number into scientific notation. And then you do that just kind of by itself without the calculations. But just watch for that if it says standard scientific notation. So I'll also do 42, just to give another example. Cobalt 2 nitrate. I should say solutions to be. And the reaction is these are 1-to-1. This is another one of those situations where we don't write the 1. So the molar ratio is simple. But I would say go ahead and break out capital M to 1 liter. Use that. I will break this one out. Solution. Use that. I would turn the 225 milliliters into liters, which is 0.225 liters, or more formally 0.22. I'll go ahead and write it down here. This is where I'm going to use it. 0.225 liters of CO2 or CONO3 to solution. So we use that. We need liters of cobalt 2 nitrate. On the bottom. So which one of those has liters of CONO3 solution? That one. So it's 1 liter to 0.175 moles CO2. That tells us we need moles of cobalt nitrate on the bottom. Used this. This is the only one left. No, I didn't write it, did I? That's from the last problem. It's 1 mole of this to 1 mole of this. So my mole ratio is 1 mole of LiS2, that is Li2S, to 1 mole of CONO3. I would still go ahead and just write these ones, even though it looks like, just to make sure the units are straight, even though it's 1-to-1. 1 mole of CO3, 1, 2S. Last point is we've got to have moles of Li2S on the bottom. That's lithium sulfide. Down here, moles of lithium sulfide, 0.125 moles of Li2S to 1 liter. Li2S solution. I'm saying solution because it's the volume. And what volume of Li2S solution? That will end us on liters of Li2S solution. 225 times 0.175 divided by 0.125. Exact. Three significant figures, so we need 3. My calculator just gave me 3, so 0.315. Solution stoichiometry. You guys okay? What else? What else do you want? What else do we have? Do you remember how to do isotopes? Pick one out. There was a mistake here before, and I fixed it now. The radium needed to have a -226 after it. There's 2 different ways you'll see isotopes written. This, actually, let me remind you what isotopes are. Awesome. Isotopes. So this is the symbol for radium. Larger molecules tend to have more. 20 ounces. There's 4 different isotopes of radium. If you look up radium on the periodic table, I'll go back to the camera. Let me show you this. Radium is all the way down here. Do you see that 88 for radium? Bottom left, Ra on the periodic table. You see the 88, do you remember what that is? That's the number of protons in it. It's also called the atomic number. So you can get that from the periodic table. So if you see this symbol, what you're seeing here is called the mass number. This is the mass number, and that equals neutrons plus protons. So this is one way you might see isotopes listed. And the only difference between these, they all have 88 protons. They vary in the number of neutrons that they have. So if you want to know how many neutrons they have, you just subtract 88 from all of them. And I'm going to do it in the calculator so I don't make a mistake. 223 minus 88. So this isotope of radium has 135 neutrons. 224 minus 88. This symbol means the form of radium that has 88 protons. These are protons. And 136 neutrons. 226 minus 88. This isotope of radon has 88 protons and 138 neutrons. And then 228 minus 88. This form of radon has 140 neutrons. You just subtract the protons from the mass number. That tells you how many neutrons. And it is that simple. I didn't go any deeper into isotopes. I'll go more into isotopes later, one more time, just to talk about atomic weight one more time. But that's what would be on the test. Oh, the other way you might see this symbol, this one's redundant. Sometimes you see it written like this. I'll do 223. Sometimes you see it written like that. And notice this is redundant. 88 and RA on the periodic table will always be together. So it is redundant. If you've got the RA, then you already know 88 protons, because you can look at a periodic table and it says 88. So then you would just subtract 88 from 223, and you get 135 neutrons. Isotopes. They'll either be written like this, or it'll be written like this, with the redundant 88 there. If you've got RA, you know it's 88. If you're told atomic number 88, you know the symbol is RAs, and you know the name of it is radium. I might have been saying radon. It's radium. RN is radon. Isotopes. Anything else you want to review? We don't have to stay. Really, nothing else? What else should I do? Practice those. Yeah, you're welcome to go if you don't have questions.
I'm sorry.
Anybody? You can stay if you want. Anybody who wants to go, just go ahead and bail out. I hope you're bailing because you feel comfortable, or at least comfortable with your study. What she's showing is doing If I didn't have so much going on, I'd do that for you guys. I'm going back to doing my accounts this week. Yeah. You can give it you should have to remember. We get to figure out what people like this.
Family still on you guys can go. Hopefully this will be Hey. Oh, you will see me there. See me there.
I'll solve that for you. I'll show you everywhere.
Checking my ear out.
And I'll give you all of this. Maybe not those, but that, that.
Okay.
Yeah, what's missing here is probably Comic-Con. Well, one of these. All that stuff. Okay. Anything that's in those charts,
they haven't emailed me about this calculations for here. So,
Because you were too late. Somebody else did that too. Responded to the email. They copied me on the email, and now because
I think I
it's
should.
going to be designed to be and we have 2 hours and 45 minutes.
I think
Purposely
I'll
designed that
have
test.
If I end up going over but I'm in here, is that okay?
Another class comes in at 5, so I can give you all the way to 5 o'clock.
Okay.
If you really need to, I guess we can do that from home.
I shouldn't.
I don't like my
that
tests to
long.
be timed. How fast can I? I just want to know if I do it, so I purposely make my tests.
Okay, thank you.
I'm literally going to pull those and I'm going to pull those too.
Okay.
But yeah, it'll be, the questions will be exactly like that, just different info plugged in. Literally the same.
On the test, are you gonna like take off points and like grade on like showing the word?
Well, when it comes to calculations, I want you to show your work.
Okay.
And as long as you show your work, you put the correct answer, A, B, C, D, or E.
Okay, but like, it doesn't matter if like we forget to write like the chemical by the by the measurement or like.
Just show me what you do. I mean, you're saying the label.
Yeah.
If you leave that out, no, I won't count off until we get that. As long as I can look at your mouth. I know how tedious it is to write these out.
Yeah.
And I know you kind of want to leave stuff off. I just always do it really formally. Then I don't mess up or don't mess up much when I'm doing it here, as long as I have all the labels. Yeah, show me the math you use to get the answer. And then I can give you credit. And if you leave some of the formality off, that's fine, as long as you got it.
Okay.
Good.
Yeah.
You guys have a question?
I'm done after survival.
Okay, so I'm done.
I'm done after that. So
Okay.
I guess I'll leave that on.
Okay.
Thank you.
All right, see you. Good luck in the session.
Well, a lot of people came yesterday. A lot more people are
I
already.
should have told everybody they can email me, but I'm going to be up north with family tonight, most of tomorrow, and then I'm going to leave Friday and go up there for the weekend.
Okay.
But I'll put a note up on detail.
Okay, yeah.
I'm still reachable.
Like, probably 15 people came yesterday to the session, and there's already 20 people RSVP'd for tomorrow.
Well, that's
So,
good, I
it's
guess.
gonna be good.
You got your work cut out.
I know, I was making the key the whole time, so it'll be figured out.
Hey, would you send me a copy of that awesome worksheet?
Do you want all of them that we've done?
Yeah, whatever you've got.
Because there's been one for
I think
every
you're the one
section.
she's got, but, I mean,
Yeah.
that's good. So.
I can send those to you. Yeah, of course.
Yeah, if you think of it, send me one. I'd like to have one.
Yeah, I can.
Also, are these the only questions that you're going for the test?
Well, there's the quizzes, and then these are the ones that don't have quizzes.
Okay.
So that's what I'm saying. Look at those two.
All right, I've done all.
Okay.
Thank you.
You want me to show you how a piecemeal thing works?
Yeah.
It works out the same. You just do it piece by piece.
Okay. Well, because like up here, I guess we did the piece by piece one, and we got the reagent, which was this one. I haven't like solved the rest of it.
All right. If I solve this piecemeal, I would go. So since it's theoretical yield,
Yeah.
you're going to pick one. And let's say we just pick potassium.
Yeah.
I would go. You want to do this one instead?
Yeah. Can you just show me like, cause she split it up, but you did it like in all.
Yeah, that's what I want to show you.
Okay.
4.39, so let's find the limiting reactant first.
Okay.
4.39 grams
Thank you.
of CO2. Sure. And then you need grams per mole first.
Okay.
Grams per mole of CO2, and that was 7.9.
Yeah.
90. I would have gone on and said moles of CO2, moles of F2,
Okay.
and that was, where's the reaction? 1 to 3 would have been 1 3. But notice, if you went 4.39 grams of CL2 over 1 mole of CL2, and you just calculated that,
Yeah.
you would have
I think it's
4.39 divided by 70. You would have, you want to keep as many digits as you can stand to write down when you do a piecemeal like this,
Okay.
so you don't lose any accuracy. Maybe not all digits, but I'll go ahead and give at least like 6 or 7.
Yeah.
6599. But if you kept all of that, and that's in moles of CL2,
Yeah.
this much equals 0.06263 blah 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 moles of CL2.
Okay.
So I could erase all that because that's what it equals.
Yeah.
And then I could go 0.062633756 blah 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 moles of CL2. And notice it still cancels.
Okay. Oh, so since
So your next step would be this.
okay.
You transfer this up here, the way I do it, I put it over 1. And then you're going to end up with blah, 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 blah,
Yeah.
moles of F2.
Okay.
And once you get that, your last step is to take your blah, blah, blah moles of F2, and your next piecemeal is going to be grams of F2, and this one is 38 grams to 1 mole. And then you end in grams of F2. So
Okay.
that's the piecemeal way of doing it.
I think I was just confused on where we got this 3 from, but we have to add the 3 because there's a 3 here. But the only reason why we didn't have to add 2s up here is because it evens out.
Yeah, she goes ahead and goes, it is, that one's 2 moles to, what is it, KOH? 2 moles of K, yeah, 2 moles of K, yeah, to 2 moles of H2O.
Oh,
And one of them's gonna be on the top and one's gonna be on the bottom, and yeah, that really is the same thing as 1 mole of K.
So that's why we didn't need to like.
These 2 things equal each other.
Okay, and that's why we have the 3 right here because there's a 3 here and not a number over here.
Yeah, well, that means 1,
Well,
1 to
yeah.
3, and this means 2 to 2, which is the same thing as 1 to 1.
Okay.
But notice if you calculate it across, you're going to do times 2, and then later you're going to go divided by 2. So those
Yeah.
do kind of cancel each other out.
So like hypothetically, if there was like a 2 right here, I know it's probably not like accurate, but it would be there would be a 2 right here.
Yes.
Okay, that makes sense.
I leave them even if they're like this, just
Yeah.
because everything's right in front of me and it's nice and clear, and I'm not.
Okay.
That just adds an extra step to me. I know it seems
Yeah.
like it simplifies it, and it probably looks like it simplifies it to Lucy as well.
Yeah.
But to me, that actually adds an extra step to me.
Okay.
I mean, if you had 4 moles of something and then 2 moles of something else, yeah, that comes down to 2 over 1, but you had to do an extra step to reduce
Yeah.
it. So to
Okay.
me, I just leave them because I'm doing it in the calculator anyway.
Yeah.
And that extends to like 6 over 3. It even means like 5 over 2. You could like divide 5 by 2 and put that up here. I mean, I just like to leave them like that because it connects directly back to the balanced equation.
And then like after we do the whole thing and we get the grams of F or the moles of F2, that's when we start finding our percent yield.
Yeah,
Okay.
I would say once you find the theoretical yield, that's when you finally boil it down to whatever significant figures,
Okay.
and then do the percent yield from there.
Okay, that makes sense.
Good.
Thank you.
Yep. And these never count as significant figures. They're significant figures in this piecemeal part was, there's 3 there and 4 there, and then you go on, and however many you have here, those are exact.
Okay.
And up here, you had 3 exact, so you still want to look at your significant figures as you went to decide where your significant figures go.
Yeah.
But that's another reason to do it all in one shot, because you see them all in front of you at once.
Yeah. And like, so for this, so question 3, finding the limiting reagent, we didn't do anything with like the 2 or the 1 here, but we just knew it was going to be this one.
Well, if you did a piecemeal, you go 15 grams of this, and 12 grams of so you did 15 and then grams per mole of H2, and then you found this, and then you used that to continue the molar ratio. And once you get the answer to that, you can do that with the grams per mole, the other thing, with the O2.
Okay.
And then you compare your results. That's how much you need, and how much you have is this.
Okay.
Maybe we should go through that, because these aren't complete the way you have them.
Yeah, well, it's like an A, B, C.
Oh, I
table.
see what she's done, okay. Yeah, so she gets you there to moles of 2 equals.
And then we multiply by 2 because there's a 2 right there, I think.
Yeah.
Will you show me how to do this one before?
Yeah, okay.
Okay.
Yeah, I prefer the long way, because everything's right in front of me.
Okay.
Instead of broken up into pieces, and then you have to keep all these ridiculous digits.
Yeah.
Okay, what is the problem? Tell me the reaction. To something,
It's 2 hydrogen 2.
H2 plus O2.
Yeah, equals H2O.
Thanks.
Or 2
2H2.
H2O.
So if I were doing this, step 1, find the limiting reactant.
And then do you also want me to tell you we start with 15 grams of hydrogen?
Yeah, so that's next. So I got to find the limiting reactant.
Okay.
I usually just pick the first one,
Okay.
and I go, okay, how many grams of H2 is it telling you?
15.
That tells you grams of H2 down here, and this is going to be the grams per mole for H2, which is 2.02. Is 1 mole of H2. That tells you you're going to need a mole of H2 down here. This is the molar ratio between H2 and O2, so we're going to do 2 moles of H2 to 1 mole of O2.
Okay.
That tells you moles of O2 down here. And this is the grams per mole for O2, which is 32
Yes.
grams of O2. And now we end in grams of O2.
Do we, wait, don't we need to multiply it by the grams they give us to, or divide it?
No, this is a comparison.
Oh, okay.
So how many grams of O2 does it say?
It says 12 grams of
The way I do this, I would have said, this is how much I have.
Okay.
Once I get through this is how much I need. And comparing these two is how you decide which one is limited.
Okay.
Let's calculate it out and see what we got. Piecemeal, you would have done this, found an answer,
Yeah.
and use that answer and calculate here.
Okay.
And once you find the answer to that, you take that answer and calculate here.
Yeah.
But I still think this is the better way to do it. 15 times 32 divided by 2.02 divided by 2. I get 120. That's exact, that's exact. 4 significant figures, 3, 3, so 120 is what I want. Okay, we need 120 grams of O2.
Okay.
Did I do that? She's got 12 up there. She probably did it on purpose. Let me double check. 15 times 32 divided by 2.02 divided by 2. Oh wow, it came out way different. Hold on. 15 times 32 divided by 2.02 divided by 2. Now I got 118.8. So this is 119.
Okay.
All right, so now you're going to compare that, and you go, this is how much I have, but that's how much I need. So what's your conclusion there?
So we have to, so this is our, O2 is our limiting.
Yes. So now we know that's limiting, and this is excess.
Okay.
And that tells us we need to use this to predict our product. So that's the next long walk.
Okay.
Find the theoretical yield. So it's step 2.
Okay.
So now we're going to use the mole ratio for these two, and we're going to start with the grams of O2 that we're given. Grams of O2 we have is 12.0 grams of O2. Grams per mole of O2 O2 needs to be down here. Now we want the mole ratio. 1 mole of O2 to 2 to H2O. That tells us moles of H2O on the bottom. And now we're going to use, it's 18.02.
Yes, that's what I have.
One mole. This is going to be your theoretical yield of H2O.
Okay.
And again, your piecemeal, you would have done this, found an answer, then you take that answer and calculate it here, and the answer to that, and you calculate it here, and that would still get you there. But saving all those numbers, I think, is cumbersome. Times 18.2 divided by 32. Exact. 4, 4, and 3, so 13.5 is what I've got.
Yeah, that's what I got on my paper, but we did the short.
Yeah.
Okay.
So they're algebraically equivalent. I just prefer this method because I feel like it's
Okay.
more succinct, but I know it's tedious.
Yeah,
so.
and then for the percent yield, it says we have 10.5 grams of H2O.
So this is our actual,
Yeah.
and that's our theoretical. So it's actual over theoretical times 100. So 10.5 grams of H2O over our theoretical is 13.5 grams. These will cancel. So 10.5 divided by 13.5 equals that times 100. Did you calculate that?
I got 77.8.
Yep.
Okay, that makes sense.
Good.
So I think it was just difficult because she like separated it into little pieces, but.
I did that for years until I started teaching, and then I started to see the elegance of doing it this way.
Okay.
So I understand the urge to do it piecemeal.
Yeah, let me take a picture of this.
All right. I got it on
Thank
video.
you, this helped.
I got it on video too. We're on video.
Oh, okay.
So everybody's going to see me show the piecemeal method, the Lucy method.
Yes, this helps. Thank
Good.
you.
All right. Oh, and I'll just say for the camera, you can email me. I'll respond. I just won't be available to meet one-on-one, but